Hi everybody. Just now we are done with magnetic dipole movement of revolving electrons. So now I am going to do a last part of this chapter. This is what we call as the moving coil galvanometers. Alright. So this is what we talk about. So far we have been dealing with current and voltage. Alright. So we talk about current electricities, we talk about currents, 1 ampere, 2 ampere, milliampere, so and forth, and we talk about voltage, 2 volt, 3 volt, 4 volt, so many voltage we talk about, but we never talk about how to measure a current in a circuit, and we never talk about how to measure voltage in a circuit, voltage across any resistors, right? So this is what we are going to do today, right? So we are going to discuss the galvanometer. This is the instruments, right? And with the help of this instrument, we would like to design galvanometer to measure voltmeter, voltage, what we call as a voltmeter. We are going to design a galvanometer to measure current, we call as ammeter, right? So this is what. So the first we would like to discuss galvanometer first, right? So the application, right? The uses of a galvanometer is to see whether there is a current or not, right? If there is a current, even a microampere currents can be detected by voltmeter or can be detected by galvanometer. And then having this, right, having these properties, this instrument is used in case of meter bridge and a potentiometer to determine null point, right? So why? Because null point is a point where you don't see any current, right? So these are the applications, right? So now as far as the construction part is concerned, the principle is concerned, right? So the principle of moving coil galvanometer is the torque, right? Torque on a rectangular current loop in a uniform magnetic field. So when you design a galvanometer, you put a rectangular coils and allow a current to pass through it, keep this natural magnetic field. So there will be a torque. When there is a torque, there is a rotation. When there is rotations, then the arrow will move and we would see we would detect a current. So this is the principle, right? The principle is torque on a rectangular current loop in a uniform magnetic fields. Now constructions. As far as construction is concerned, it consists of a scale which help us to note the numbers, right? Then it has two permanent magnet. This is one is south pole. One face is the south pole. Other face is the one face is the north pole. Other face this is facing toward south pole, right? And then we have a cylindrical iron core. This is a cylindrical iron core, soft iron core. This is what the shape is, a cylindrical iron core. And there is a reason why this should be a cylindrical iron core. That means if it is a cylindrical, every time magnetic moments, the magnetic field's direction is magnetic field direction. The coil is always along a direction of magnetic fields. Coil is always along a direction of magnetic fields. So therefore, direction of magnetic moments and direction of magnetic fields are always perpendicular to each other. Therefore, torque is going to which? Torque is going to be always IAB. Alright, torque is always going to be IAB, right? Torque is always going to be IAB. Alright. Or I say this is going to be, if I have n number of turns, this is NIAB, where theta is always 90 degree. Why theta is always 90 degree? It is a radial magnetic field, right? So since this is a cylindrical iron core, this allow the field, this allow fields, right, always radial to the coil, If it is radial to a coil, then angle is going to be 90 degrees. So this is the significance of or cylindrical iron core. And another significance of a soft iron core, cylindrical iron core, is that when I put a soft iron cores, that it increases the magnetic field strength. It increases the magnetic field, so therefore torque would be more. So and then I have and this is the springs which I fix at iron core, and why? Because when it rotates, these springs provides a counter torque. These springs will provide a counter torques. This spring will provide a counter torques. Alright? These springs will provide a counter torque, so that when you remove a current, it will come back to its original, that is zero, right? So this is what, so these springs provides a counter torques so that this stays in balance, right? This, the arrow stays in balance, right? A pointer stays in balance at certain point depending on the magnitude of a currents. Alright, so these are the point, right? So radial magnetic fields, uniform radial magnetic fields, alright, and then this is the permanent magnet, core, a cylindrical iron core, soft iron core, pointers, scales, so on, right? So this is what we have. So construction part is that n turns of coil free to rotate about a fixed axis in a uniform radial magnetic field. There is a cylindrical soft iron core which not only makes the field radius, right? This is the role, this is the significance of iron core, right? Cylindrical iron core, and also increase the strength of fields, right? And then again I tell you, SP is a spring that provides a counter torques, right? Now, the application of this is to detect current in a circuit, and it is used in a meter bridge and potentiometer to determine null points. So these are the applications and constructions and the principle of galvanometers. So now this is what we have, right? This is the galvanometer, all right. This is north pole, south pole, iron core, and there is rotations are done, and then this is the mirror upside. This is how it is done, right? Iron core. This is another diagrams of galvanometer. Now this is one, right? So this is a galvanometer, and this is an ammeter, and this is a voltmeter, right? So this is the principle, right? Having this, I can convert this into ammeter, I can convert this into voltmeter. So we will do this also. Alright. Now I would like to do a walking part. Alright. So the torque experienced by coil of n turns is NIAB. This is the torque. Why? Because since it's a radial field, then theta is always, since it is always radial fields, theta is 90 degree, hence torque is, this is the torque. This is torque experiment. And now I have spring SP provides counter torque, alright, that is how much is the counter torque. This is equal to, proportional to, let's say it's on phi, alright, some angle deflections. So therefore this is equal to K phi. Phi is a deflections. This is a deflections. And K is torsional constant, right? Spring constants. So I say that, so since this springs provides a counter torques and has a balance points I mean, since this provides the counter torques, so this provides the pointer will stays at balance, right? This balance at particular point, right? So it has a balance points. All right. So that is equilibriums. That is at equilibriums. That is at equilibriums. All right. K phi is equal to NIAB. This is at equilibriums. So now what I have is this is phi is equal to NAB divided by K I. This is what I have in case of galvanometer, right? So this is the terms in the bracket is constants. These are the constants. And is a number of terms which is constants for particular galvanometers. A is the area of a coil, B is the magnetic field, K is the torsional constant. So this equation tells that deflection is proportional to currents. Deflection is proportional to current. More current, more deflection. It appears this gives more deflections. Alright, so this is what we have. And then now this is the principle, right? Now this is the working, right? This is the working, right? So phi is directly proportional to I is working. So more current, then this gives more deflections. Alright. So now I would like to do a current sensitivity, right? So current sensitivity is defined as a current per unit deflection per unit currents. Deflection, the ratio of deflections and a current is what we call as current sensitivities. So current sensitivity is constant for particular galvanometer. This is current sensitivity. This is current sensitivity, and this current sensitivity tells us about, about the sensitivity of a galvanometer for a current, right? So if a galvanometer deflects even at a microamperes or a microampere, then I say that sensitivity is high, right? If a galvanometer doesn't deflect in a microampere, then the sensitivity is less, right? So this is what I have. And then voltage sensitivity, and now voltage sensitivity is defined. Alright, so I'll bring first current sensitivity. So divide and multiply this, just divide by R. Alright, IR is nothing but V. This is the voltage sensitivities, right? This is the voltage sensitivities. So the voltage sensitivity is deflections per unit voltage. Deflection per unit voltage is voltage sensitivity, and deflection per unit current is what we call as a current sensitivity. And then again, frequently asked in exams, it is not necessary that if current sensitivity increases, voltage sensitivity has to increase, right? So if I increase the current sensitivities, all right, every times voltage sensitivity will not increase. If I increase the current sensitivity, every time voltage sensitivity did not increase. All right. So the example I would like to give you is if I increase the N, then current sensitivity is going to increase. Current sensitivity is going to increase. However, look at the voltage. I increase N to N. However, I is also going to increase. Or if I increase the length, if I increase the end, length is also going to increase. If a length is going to increase, the resistance also going to increase, right? So therefore, in this case, so this is the case, right? Alright, where current sensitivity is going to increase, but voltage sensitivity does not increase. Alright, so if N goes to N2, voltage current sensitivity is going to increase or double, right? And however, voltage sensitivity remains same. Why? Because if N increases, R also increases. So therefore, the ratio remains same, right? So this is for voltage sensitivity and current sensitivity. So now my job is, can I use galvanometer for finding current? If I say no, reason, right? So this is what I am going to do now. So galvanometer cannot be used as ammeters. So that means we cannot use galvanometer for finding current. So why? Reason, right? Why galvanometer is not fit for finding current, for measuring currents, right? I have written only 2 points, very simple points. Galvanometer is very sensitive device, all right, and it gives a full deflection for current of the order of microampere. So even the current goes to a few microampere, this goes full deflection. So therefore, this is not at all used for finding milliamperes. And in day-to-day life, we come across 30 milliampere, 40 and 1 amperes. So it is not at all used. Another point is that it has a finite resistance. It has, so normally, how to find current, right? So if I say this is a resistance and this is a very simple circuit. I would like to find our current in these circuits. If we would like to find our current in this circuit, how to do? Very simple. I connect ammeter. This is so if I connect the galvanometer here, and galvanometer has a finite resistance. If it has a finite resistance, alright, before I connect the galvanometers, alright, then the current is equal to V by R. Current is equal to V by R. This is the resistance of this wire. Now, after connecting, galvanometer, look at here. After connecting galvanometers, let's say galvanometer has resistance Rg. After connecting galvanometers, now current would be equal to V divided by R plus Rg. So which is this is much greater than this. So it is not at all used for finding out the current, right? So now what to do? Right? So the problem is having a finite resistance. So how to make this resistance very small? How to make this resistance very, very small, right? So very simple is that I'll be having a galvanometer having a resistance Rgs, and what I'm going to do is I'm going to connect a very small resistance called a shunt resistance. This is called a shunt resistance. So how to make galvanometer into ammeter? How to make galvanometer into ammeter? Alright, connectings. So here shunt resistance RL parallel to galvanometers, right? Parallel to galvanometer, right? RG means galvanometers. So connecting shunt resistance RS parallel to galvanometer. This is what we have. So now this entire setup is what we call as ammeter. This entire set is what we call as ammeter. This is ammeter, right? If it is so, now look at here, resistance is going to decrease. Look at here. What is the net resistance? Resistance is parallel 1 by equivalent resistance is going to be 1 by equivalent resistance is equal to 1 by Rg plus 1 by Rs. So Rg is equal to Rg Rs Rg plus Rs. So this is very small compared to Rg. So equivalent is almost equal to Rs. So this resistance becomes very small. So this is how we use it. Now how to find out this? So we have a ammeter of different range. 30 milliampere, 40 milliampere, so many ranges are there, right? So how to find out the different range? So the different range of ammeter is defined by shunt resistance. I'm repeating, right? The different range of ammeters are defined by shunt resistance. Look at here, I'll see, right? This is the current. Let's say this is the current. This is the current. Let's say I is the range of currents. Range of currents that is range of current of ammeters, current of ammeter, all right, and Rg is resistance of galvanometer, and Ig is the current in, that is the maximum current, right? Maximum current in the galvanometers. Range of current in galvanometers. Now we will find out. Look at here. This goes like this, and this is Ig, I minus Ig. All right. So therefore, Rg. This is a suffix. Rg is equal to I minus Ig Rs. So we would like to find out Rs, right? So this is equal to Ig Rg divided by I minus. So this is how we are going to find out. This is how we are going to find out. So depending on the range of currents, these two are constants. Depending on the range of current, Ig is going to change. If a range of current is high, then Ig is going to be less. If a range of current is low, then Rs is going to increase. So this is what we have. All right. So this is very, very important equation, right? And this tells us how to convert a galvanometer into ammeter. And this is the shunt resistance of an ammeter. So you are going to connect Rs in parallel with galvanometer, and this is how you convert galvanometer into ammeters. This is the one part. Now the second part is how to convert galvanometer into voltmeter, right? So we say that voltmeter, we are not going to use voltmeter, we are not going to use galvanometer for finding a voltage. All right. Why we are not using galvanometer for finding voltage? I will tell you now. All right. So how to find a voltage? We connect parallel, right? So let's say I'll give you an example. This is resistance R. So I'm going to find out voltage. This is the voltage. This is how you are going to find out voltage. And if you use a galvanometer, look at here. If you use a galvanometer, you are going to put Rg, all right? and there will be a current. And look at here, if I say before I connect this, there will be current I, and voltage is equal to IR before I connect. Alright, and when I connect, now when I connect a galvanometer to measure voltage, this is IG, this is I, this goes in these directions. So there will be, this is not going to be I, right? Alright, let's say this is I prime, right? This is I prime, this is if I prime, then I minus I prime. So what about voltage, right? And voltage would be equal to I prime into R, which is less than V. So this is not so, right? So the voltage measurement will disturb the original setup by amount which is very large. So this is good. So normally whenever we use the device, this actually disturbs the measurement. However, the disturbance are only of less than 1%. If it is less than 1%, then measuring device is okay to measure things. If it is 20%, 30%, if it is something like 50%, so the measuring device is not suited for measuring a particular physical quantity, right? So this is what exactly happened in case of galvanometer, right? So what is the problem, right? What is the problem, right? So I is less than I. So the problem, this is the problem. So how to fix the problem, right? This has to be almost equal to I. This has to be almost, this is how we are going to fix. Alright? How to make I almost equal to I prime almost equal to I? I will make this very big. If I make this very, very big, the current passing through would be maybe less than 1%. So therefore, this is alright. So this is what I'm going to know, right? I have a galvanometer like this. This is a galvanometer. So I'm going to put a very high resistance R. Very high resistance R. Alright. Now this become a voltmeter. This become voltmeter. This become voltmeter. This become voltmeter. Alright. Now what I'm going to do is, now look at here. Now the total resistance, equivalent resistance is equal to Rg plus R, which is almost equal to R. Why? Because R is very much greater than Rg. So this is what we have. Right? So now how to convert, right? So again, we have a different range of voltmeters. Alright, I can have a different range of voltmeter. And how are we going to fix a different range of voltmeter? And what factors differentiates a different range of voltmeter is the factors. Resistance, high resistance. High resistance R makes the difference. High resistance R differentiates a different range of voltmeter. So this is what I have, right? So how to fix this? Alright. I'll be having this. V is the range of voltmeter. Let's say range of voltmeter. And Ig is the current, galvanometer current, range of current, right? Range of current in galvanometer. And then what else? Then Rg is the galvanometer resistance of galvanometers. Alright, now V is equal to what? V is equal to Rg plus R. Okay. This is what I have. This is the range of voltmeter. Alright. So V Ig Rg plus Igr, this goes this side. So I Rg equal to Ig Rg. I'm sorry, this is going to be like this: V minus Ig Rg. All right. So therefore, R is equal to V minus Ig Rg equal to Ig, and this can be written as V by Ig minus Rg. So this is the answer. Look at here. Now, if I increase the voltage, the resistance is going to increase. All right, resistance. This is the fixed, and this is the fixed, and these two factors, right? So, depending on R, capital R, that is the resistance, high resistance, which determines the range of voltmeters. The range of voltmeter is all determined by high resistance. This is what we talk about, what we have discussed in case of ammeter, right? So this is the diagram we have here. All right, galvanometer resistance and high resistance. All right, so this is how, and maybe next I will send few problems related to how to convert galvanometer into voltmeter. All right. So with this, we come to the end of this chapter, chapter number 4. All right. Thank you.